Okay.
Okay.
We will start with that question that we had the other day. Somebody wanted me to explain parity. You were the one?
Yes,
Yes.
sir.
Yeah, I know. So let me explain it more clearly now. We usually add an extra bit to the data. Data can be 4 bits, 7 bits, how many number of bits, it doesn't matter. Number of bits in the data string. Let us say ASCII has 7 data bits. Now we will add an 8th bit, MSB. This will be 7 bits. This MSB will be the parity bit, most significant bit. We have to define whether we want odd parity or even parity. We can choose that. The choice is yours. So let us say I want even parity. The number of ones in the data string, including the parity bit, should be even. Such a description is called even parity. So I will give you an example. All are zeros. 7-bit data is zeros. This is see, there are 0 ones. 0 is supposed to be even number. 1 is an odd, 0 is even. Usually that is what the assumption is. Usually assume 0 to be even. So since already there are even number of zeros, I add 1, another 0, this becomes parity bit. The total number of ones in the bit stream is 0, which is even. One more. Suppose I have my data 1 0 1 0 0 0 1. Now it is even number, odd number of ones, 3 ones. 3 is odd. So I will add a 1 here, so that the total number of ones become 4, which is even. So always when the data goes out with the parity bit, the number of ones should be 1, number of ones should be even in the string. Another example, extreme example. There are 7 ones. 7 is an odd number. I add a 1 to it. So the total number of ones becomes 8, which is even. This is what is known as the even parity. Odd parity is the complement of that. Total number of ones including the parity bit should be odd. We will take the same example of zeros. Number of ones is 0, which is even, but I want total number of ones as odd in a bit string with parity, so I will put a 1 here. So that the total number of ones is odd. If we take the second example, already number of ones is odd, so I put a 0 here. So total number of ones in the bit string is odd, which is 3. Okay. parity bit. See, you define the parity as odd or even before transmission. The receiver counts the number of ones. If the number of ones, supposing you define as even parity, and if you send a message word by word has no definition. You get 7 bit and 1 parity, 15 bits and 1 parity, 4 bits and 1 parity, whatever is your data format, doesn't matter. Because the receiver and sender have synchronized this information already. My data consists of 7 bit words followed by parity, or 15 bit words followed by parity, like that. So now you define my parity to be even, and I count the number of ones on the receiving side, it becomes odd. That means you know there is 1 bit lost somewhere, or 1 bit it has picked somewhere. So there is an error there. There is an error in the parity. So you have no way of correcting it. It is only error detection code. Parity is only for error detection. No way of correcting it, except tell the other guy, the sender, there's an error, so please resend the message. Usually they don't do it every bit. Every word, data word, they don't say that. The messages are packed as some data strings. Let us say 16 words. At the end of 16 words, they will say even if one of these words is wrong, you will ask them to repeat all the 16, because it is not possible to say every time there is 1 bit missing, 1 bit missing, and your total communication is delayed. Instead, after receiving the number of words in a frame or whatever they call it, if you find there is a parity error, so 1 word or multiple words doesn't matter. There is a parity error in the message you have sent just now, so repeat it. There is only recourse to this. This is all right for certain simple applications, but error correction is very important, because when you do not know the source of the data. Suppose you pick up a satellite signal and just start analyzing it, there is an error. How do you know what is the source? How do you know what is the number of parity bits they use and all that? Of course, they will tell you the parity bit, who is the person to whom you should contact. So what you do is, now there is an error detection. There are lots of codes. It's a big theory. Coding theory is a very big subject in communication engineering, networks. That is not the scope of this lecture. But what they do in error detection is, they have multiple things. They will have one simple example would be to align all the words of the data, count the number of ones in columns, count the number of ones in rows, then there is some relationship, and if it doesn't satisfy, there is an error. You have to discard it. It is not always that it is possible to send the information to the sender and say correct it. Sometimes the data is useless. We have no choice. Especially the unknown source, the data is coming, you have no choice. You have to discard it. That's it. But lots and lots, the subject has grown so much, very efficient techniques are there so that you can detect and correct. One of the simplest codes they use in correction is called hanging code. I am not going to talk about it. One example. There is so much for parity. Any questions on that? Parity? Okay? Okay, good. The other question that day was overflow. What is an overflow? See, you add numbers. Say the arithmetic unit, and you add numbers in what is known as the accumulator. I hope you all have microprocessor background, or you will learn soon. You add numbers in a hardware is called accumulator. Accumulator has 2 inputs and 1 output. two inputs add. So supposing we have a 8-bit data, 2's complement. 1 is sign bit, 7 is magnitude bits. So 8-bit 2's complement, I will talk about overflow now. Eight-bit system. So I have A and B as 8 bits. No, 1 is not the sign, it is sign bit, and because 1 is negative number, so assume sign bit. I will put S. I will put S and M. S is sign bit, M is magnitude bits. Now we are going to add them or subtract them, or add one from the other or subtract one from the other. So if A and B are both positive, and if the result comes as negative, because the sign bit is 1, when the two numbers have sign bit zeros, and I add them and find the number 1 as the sign, something is wrong. I cannot add two positive numbers, get a negative number. So when A and B are both positive and result is negative, or the other way, if A and B are both negative, and the result positive, this also are sure, -1 from -1 plus -2 is -3, not positive, it cannot be positive. So two numbers added, both are sign positive, now result should be positive. Two numbers are negative, you add them, result should be negative. If the result is something differently, it is because overflow. What is an overflow? My 8-bit number is sign bit 1, 7 magnitude bits, minus 128 to plus 127. I already told you that. In 2's complement, you have 255 representation, including 0 is 256 representation, which is not possible in 1's complement and sign magnitude. Sign magnitude 1's complement have 2 representations for 0, so the result is only 250 minus 127 plus 127 0. So 255 the variations are possible. In 2's complement, 0 is represented only once, so I can have minus 128 to plus 127. Now I am having an 8-bit register in which I add A and B, push the result into an 8-bit register, and the result is more than the magnitude of the. So the magnitude can be positive or negative, that is the sign. But once the sign is fixed, the number should be either 0 to 128 or negative if it is negative, or 0 to 127 if it is positive. If you try to push a number greater than this into the register which is supposed to take the result, then the number will not be right. So that is called an overflow error. You can detect this overflow and then scale your numbers A and B to make it smaller and add them to get correct results, and then you know how much you scale. Suppose I ask you to add 100 plus 100. 200 cannot be represented in 7-bit magnitude. So you reduce 100 by, divide 100 by 2 to 50, divide the second 100 by 2 to 50, add 100 plus 100 is 50 plus 50, the result is 100. Overflow error will not be there, but you know that since you have divided everything by 2, finally when you take the result, you multiply by 2 and take it as 200. That is one technique. So this overflow error is because of you are trying to push in a number which is larger in magnitude than the magnitude capability of the register into which the result would go. How do you detect it? That day we gave you some simple example. So what we do is, this is the rule. But how do you find this? Because the computers don't know. You give a bit string, 8 bits. You assume one is positive number, one is negative number, one is the sign bit, the rest 7 are magnitude bits. All that you assume. Computers know it. For it, there are 2 bit strings, and they are asking to make an adding operation. It adds and then gives you the result. You should know whether it is right or wrong. Computer will not tell you it is the wrong result. But you can find out it is the wrong result by introducing what is used overflow error, overflow flag. This overflow flag, what it will do is, if the last carry in Cn, see this 8 bits, so I am going to start with, let us say some 7 numbers, 7 bits, and you add them, carry 0, carry can be 0 or 1, I don't know, carry. The carry going in into this and carry coming out of this, so finally also there will be a carry. The carry going into this and carry coming out of this are different, then there is an overflow error. That is a detection mechanism. So we will call it Cn minus 1, C for carry out. Cn minus 1 exclusive OR, we will talk about exclusive OR gates today. Cn is overflow bit. If this is 1, there is an overflow flag I will put. Overflow is there. If it is 0, no overflow. That day I gave the example of 2 numbers. I don't know what numbers I gave. I was using 4-bit numbers. Today I will give an example of 8-bit numbers. Minus 84 minus 107. The result should be, if you add them, should be minus 191. Decimal arithmetic, you know this. Now, 7-bit magnitude is 1-bit carry. So 7-bit magnitude can only be at most 127 positive or 128 negative. Number is more than that. So you are sure to get a carry. Sure to get a overflow. So if you do this numbering, I will not do the entire arithmetic, I will just represent these numbers in 2's complement form. I will write here. 2's complement form, including 7-bit, this is minus 84. This includes 7-bit. 2's complement number of 2's complement representation of minus 84. This is 2's complement representation of minus 107. Add these numbers. In 2's complement, subtraction in 2's complement is addition. Subtraction is 2's complement, addition in 2's complement. So if you add this, 1, 1, 1, 1, 1, 1, 0, 1. This carry we discard, the number is right. The number is right including the 7-bit. This carry anyway will discard in 2's complement, the last carry overflow bit. That we will discard anyway, we will not use it. But what I meant was, the carry going in is 0, carry here is 0, this is Cn minus 1, this is Cn. Cn is 1, Cn minus 1 is 0. So 1 and 0 putting exclusive OR operation gives a 1 which is overflow bit. So Cn minus 1 plus exclusive OR Cn is 1. So I can say it's an overflow error because Cn minus 1 Cn is 1. That proves by a result 191. 191 is shown, which is overflow already, we know that. So this is what it is. Okay, these are the two questions which were asked the other day. I thought I will explain once more. Any questions, you can raise your hand and I will ask somebody to unmute you. Because I am going to switch to a new topic. Any questions? Show up your hands. If you show up your hand, I will request the editor to unmute you. No questions? Good. You understood everything? That is fine. Okay. See, it is not a discourse, religious discourse. You go to the temple, some Panditji keeps talking, you like, you stay, if you don't like, you get out. The next day you are busy with the entertainment program, the television, you bunk the religious discourse. This is not that. If you are interested in studying and learning a subject, you should attend all classes. You should prepare with the number of lectures I asked you to prepare, come prepared with. You should do all the assignments. You should take the test. Because it is free, does not mean, and because this is not going to affect your result in any way, or your CGPA or whatever, at the end of the course, it does not mean that you can just walk in and walk out like it's, as I said, a Puranic discourse by a learned Panditji in a temple. I am not a learned Panditji, and this is not a temple. Okay, I am a learned professor, this is a temple of learning. Okay? Yeah, please remind this to other friends who have been coming with you. There is no point in telling the people who are already here. That is what happens. I speak to people who are already there about how to come. Because we are already there. What is the point in my telling you this? But I have no way of accessing others. Maybe you can send them an email, Mr. Krishnan. Kannan. Send them all an email.
Yes, sir.
We are going to be so irregular, they will be sorted out of the program. Yes, it's not. You see, they have to take it seriously. How much seriously I come, prepared all the questions you ask, I am preparing the answers, the examples, and these fellows don't come. Let us move on. See, I told you to come prepared with next 2 lectures in NPTEL, which is I think 3 and 4, is it? 4 and 5. I forgot. Anyway, now, these are on logic gates. Logic gates, formation of logic gates into simple circuits, how to write the truth table, how to produce a logic circuit for a given function, etc. These are basic gates. First we will just review them quickly. See, all the digital electronics can be converted to hardware by simple gates, and these gates are very few in number and very easy to understand. Even a most complex digital signal processor or a most complex Pentium computer, if you break it down, I think the other day I gave you the hierarchy of higher level, subsystem, modules, circuit level, gate level, transistor level. If you have a hammer and break your Pentium processor, it will not be useful to you anymore, and you won't see the transistors. I am just giving you a sort of a exaggerated picture. There will be transistors and transistors and transistors. These transistors are usually CMOS, complementary MOSFETs. So we will not go to that level. The next level is these gates, these transistors are formed as gates. So these basic gates are everywhere. We have a field programming gate array. A gate array, million gates will be given to you on an IC. You can connect them any way by using programs. These gates form subsystems, adders, subtractors. And then the subsystem forms modules, arithmetic unit, logic unit, shifting unit, and so forth. And you combine all of them to get a microprocessor or a computer or a cell phone or whatever. So basically you should know gates. Nothing less than gate, even gate less than gate is transistors, CMOS, they are called devices. You leave the devices out. At the start of the gate circuit, gate level, everything that you see in digital electronics, a display in a bank counter, a railway reservation system, your hi-fi video, audio, your cell phone, everything is made up of gates. But nobody builds gates and then builds it. Becomes a lot of problem. When you connect gates, there will be errors because of disconnection, because of dry soldering, and then huge volume to occupy. You will consume extra amount of power. So we reduce it to modules, sub-modules, all that. So what are the basic gates? First is NOT gate. NOT gate is also known as inverter. You have one input, one output with a bubble, a triangle in the horizontal direction, the bubble at the tip is called inverter. Let us say this A as signal input. We are going to use A, B, C, F like that. That's all. No numbers now, 0, 1 and all are not used now. This will be A bar. Means if A is 0, A bar is 1. So the truth table they call it. Inverter truth table. F is the output. If input is A, output F is, if it is 0, it is 1, 1 it is 0. Or A bar, A is A bar, this is A, this is A, this is A bar. This is simplest of gates, you need it. Many times you want to signal, invert the signals. 2. AND gate. 2 inputs, 1 output, A and B as inputs, F as output. This is called truth table. This is called the symbol. This is called the symbol of the gate. This is called the truth table of the gate. It only speaks truth. That's why it's truth table. 0, 0, both inputs are 0, output 0. One of them is 1, even then output 0. When both are 1 and only then output is 1. This is called an AND gate. And the expression for this is F is, here F is A bar. Here F is A and B. AND is given by a full stop there. But as you go along, you will forget to put that as doesn't matter. So you will put it as AB. This is an operator. This is called AND operator. As you go higher and you forget to put this dot, doesn't matter. F equal to AB will say, which is understood as A and B. You read it as A and B, but in a hurry we will always say F is equal to AB, it doesn't matter. Then the OR gate. Either A or B. Also what's the symbol? No, I am not going to give us now everything. This is symbol, this is input, this is output, again A and B. F, truth table will be 0, 0, 0, 0, 1, 1, 0, 1. This is opposite of AND gate, not opposite exactly, because at least one of the ones is 1. At least one of the inputs is 1, the output is 1. So this is called A or B. OR is the operator, the plus sign is the OR operator. Not the arithmetic plus. You don't add A and B, you find out A or B. You have to read it as A or B, but generally people don't read it A or B, they write A plus B. That's it. As long as you know what you are doing, these are minor things you can forget about. Then there is a NAND gate. Okay? Can I talk now? Studio. What is happening? Are you able to hear me now? Okay. There is a glitch somewhere in the audio. Okay. NAND gate, we have two inputs, on output F. This is exactly opposite of, this is the opposite of A, complement they say. We don't say opposite in digital. We say complement. This is AND gate complemented. That's why it's called a NAND. No AND. Not AND. Not AND is NAND. So here, AND gate you see zeros and 1, ones and 0. Symbol is exactly same as AND gate with a bar on top. Anytime you put a bar, it is the inverted signal. So you can easily see that NAND is AND with an inverter. This is same as this. Or the reverse. If I have an NAND is an inverter, I get AND. This is AND, or this is NAND. This is, because the inverter is another inverter, two inverters get cancelled. Then there is a NOR and OR. Already talked about OR. NOR is AB, NOR symbol is R with a bubble. AB, F, F is A or B, bar. A or B bar, which means I will exactly the opposite of or complement of OR gate. In truth table when you write, you have to follow certain principles. Otherwise you don't know what are the combinations you have written, what are the combinations you have left out. Because it's only two variables, we can easily write 4 rows. 0 0 0 1 1 0 1 1. Suppose you have 3 variables, that will be 8 rows, 0 0 0 0 0 1 etc. 4 rows 16 like that, 4 variables 16 rows. So you always start with LSB, LSB 0 1 0 1 0 1 0 1. Next bit 0 0 1 1 0 0 1 1 0 0 1 1. Then the third will be 0 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1. Fourth will be 8 zeros followed by 8 ones. Fifth will be 16 zeros followed by 16 ones. That pattern if you adopt, you will not make a mistake of omitting something, and all the lines will be covered. And also when we use it for simplification purposes, it will be very useful. I will show you that at that time. Now this again you can follow from OR gate by providing an inverter. This becomes ARB, or you take an OR gate, put an inverter, this becomes ARB bar. And finally there is one more gate called exclusive OR gate, which is very frequently used, very elegant gate. It's called exclusive OR. This is called inclusive OR. We don't say that. This is inclusive OR. We don't say inclusive OR, we say OR. This is exclusive OR. That means it has two inputs, same as OR symbol, with an extra arc, the gap. OR symbol with an extra arc and a gap. This F is written as A or B. The OR symbol is, put a round, put a circle around the OR symbol. This is called exclusive OR operator. Truth table is either one of them should be, if both are zeros, output is 0. If one of them is 0 and the other is 1, it will be 1. If both are 1 again, it will be 0. This is different with this. This one, if only one of the inputs is 1, we will have an output. If all the inputs are 0 or all the inputs are 1, we don't have an output. Here, at least one of the ones should be 1, one of the inputs should be 1, then we will have an output. That is the difference. Naturally, exclusive NOR is the opposite of that, XNOR. This is same as exclusive OR symbol with a bubble. Bubble always inverts, bubble at the end always tells you there is a inversion. And it is written as F is A exclusive OR B whole bar. That is the operator. One other nice thing you can see in exclusive OR gate, NOR gate, two inputs are same, the output is 1. It is also called coincident detector. If both inputs are same, the output will be 1. If one of the inputs is different from the other, the output will be 0. This is called coincident detector. We will draw some simple circuits using these gates and then tell you how to interpret the equation, and later we will see how to simplify that. When you have a first round, you don't know how to simplify, you write the whole thing. Then later on you find some of the gates redundant, not necessary. At that time we will simplify into it. There are lots of procedures in simplification, but we will only adopt the simplest of them, called corner maps. Now, before we go there, I want to tell you any logic function can be followed by, because NAND gate is only AND and OR. NOR gate is only or and not. And is not, NAND is and and not. NOR is or and not. So and or not is enough. NAND and NOR are not required generally. And exclusive OR is again, this is both, you can write this as A bar B or A B bar. So another way of expressing this F A or B is A bar B or A B bar. That means if A is 0, B is 1, or if A is 1 and B is R, both cases the output is 1. So again these are AND gates with an inverter and an OR gate. 2 AND gates, 2 inverters, 1 OR. This is also like that. This is A and B or A bar B bar or A B. This is an AND gate, 2 inverters, it's an AND gate with 1 OR gate. So all the gates can be given in terms of AND or invert. These 3 gates are essential gates. You cannot knock one of them and get any circuit that you want. Any circuit that you want in digital, whether it's a combination logic or sequential logic or microprocessor, whatever digital circuits design will consist of AND or invert. But to make it life even a little simpler, we will see that each of these AND or invert can be formed from one single gate called NAND gate. NAND gate is not derived. A, B and C, AND gate, OR gate and inverter are called fundamental gates. Fundamental gates. This is AND or invert. Fundamental gates are AND or invert. NAND, NOR, exclusive OR are called derived gates. This is a derived using AND or invert. Are you able to see here when I write? Are you able to see here? Say yes or no by hand. Yes. Otherwise I will write on the top. See, I am short, I can only reach this much. Derived gates. But even when you unmute it, they should be able to show their hands. That is what they don't do. Derived gates are NAND, NOR, XOR, XNOR. What I am trying to say is, the entire digital electronics hardware can be reduced to AND or invert gates. All other things are not required. But then life will be very miserable. Everything you have to do in terms of this and this and this. So that is not the right way to do it. We will go to some other forms of doing it. So next topic, I will say, again the same topic continued, next subsection will be what we call universal gates. We have not seen about half a dozen gates. And I said 3 of them are fundamental, rest of them are derived. 7, 3 plus 4, 7. Now, There are two gates which are chosen from the 7 which have a unique property. These are called universal gates. I told you all the digital functions can be represented in terms of AND or invert. NAND and NOR are not required, but then we have to do extra work to get them. But we can even make it simpler by defining what are known as universal gates. NAND is one of the universal gates. This is NAND gate, I think you remember now. This is a given NAND gate. Can I get this gate to work as an inverter? We will see. Supposing I tie these two inputs together and apply A here. What is the truth table? This is the truth table of NAND gate. Now, since A and B are same, I don't want these two lines. A is 0, 0 or 1, 1. B, AB is 0, 0 or 1, 1. So, when this is 0, output is 1. When this is 1, the output is 0. So, the output will be A bar. If you give a 0 here, the output will be 1. With a 1 here, the output will be 0. So, I can get an inverter from a NAND gate by tying together the two inputs. Okay? AND gate. I take a NAND gate again, put an inverter here. This is A or B, A and B bar is inverter. So, this is NAND inverter becomes AND. So, I get a NAND gate, two NAND gates. This inverter is nothing but just now we showed that this is same as that inverter. Third one, we want OR. This is A, this is B, this is A bar, B bar, this is A bar, B bar, over bar, because AB whole bar becomes A bar, B bar whole bar, A bar, B bar whole bar is same as ARB. That we will see later in Boolean algebra. It's called De Morgan's theorem. If you already heard it, fine. De Morgan's theorem you heard, right? So, De Morgan's theorem says A bar and B bar whole bar becomes ARB. So, I have an OR gate out of NAND gate. This inverter again NANDs. So, one NAND gate become an inverter, two NAND gates become an AND gate, three NAND gates become an OR. So, that is, I told you A, B and OR and inverter are the fundamental gates that are required for defining any logic function, implementing any logic function. Now, these three I can get using NAND gate itself. So, NAND gate can replace AND or invert. Even though it is a derived gate, from AND we got it, AND and invert becomes NAND, but NAND is a universal gate. So, NAND is called a universal gate. I leave it to you as an exercise. You see my video, NPTEL video on this. How NOR gate is also a universal gate. I am not going to talk about it now. Similarly, so NAND and NOR are universal gates. That means if I am given enough number of NAND gates, I can get any logic function you want. If I am given any number of NOR gates I want, one of them it's enough, not NAND and NOR. You say I will give you 100 gates, 100 NAND gates, provide this function. I will try to provide it. I will not say NAND R is missing, AND is missing. The function you gave I will not be able to recognize, implement with 100 gates, and you need more gates. That case I will ask you for 50 more gates. Otherwise I can do it. Similarly, if you give me 100 NOR gates and ask me to implement a function, I will try to do it if it is possible. Otherwise I will ask you for more NOR gates. I will never go and ask you give me an AND gate, OR gate, NOT gate. That is why these gates are universal gates. Now why is it important? Why do we have to do all these gimmicks? The gimmicks is because, see, VLSI technology is there. You should not forget we are talking about high tech, very large scale integrated circuits. What you see in your cell phone, I don't know how many of you have seen the cell phone inside the circuit inside cell phone. Very little components, out of which one small component called the core of the cell phone. You break, as I said, you open a microprocessor, you open a computer, one chip is microprocessor chip, Pentium chip. All of those are required for peripherals. You break any electronic equipment, of course you are responsible for the damage, I am not. So, look at it, there will be one small function, one small device. That device should hold, now I told you there are million gate functions are available. I don't know Pentium has how many gates, I can tell you later if you want all that. It's all available in Google. I think Google is your best friend. All of you know how to Google, I know that. So you want any answer, in fact sometimes I don't know the answer to the question, I go to Google and tell you. What is there? There's nothing wrong. So Google it, find out how many inverters, how many transistors are there in the Pentium processor, or how many gate equivalents. It's not gate actually, it is not AND gate, AND gate, AND gate, AND gate, NAND gate, NAND gate, NAND gate, all NAND gates, no. They replace this by different functions, but what is the gate equivalent, they will tell you. For each circuit they will say this is equivalent to 10 gates, this is equivalent to 27 gates, equivalent to 100 gates. So what is the gate equivalent? So millions. So I can't be doing this with different gates and all that, they have to be packaged so nicely. So it's better to have only one gate manufactured. The processor VLSI at the end of the day, all the circuits to be reduced, as I said, to gate level, system level, subsystem level, body level, etc. Gate level, less than gate level is transistor level. I am not going to go into that. You don't make a NAND gate directly, you make NAND gate using transistors. We leave that part out, it's the device people's part. So all of these can be made with one single IC, makes it efficient design and efficient manufacture. So that is why they call the concept of universal gates. Most of these logic functions, big functions, systems, they will reduce it to all one type of gate so that the manufacture is easy. It is something like packing a suitcase with same identical type of material. Suppose you are packing a suitcase to go home, all odd things will be there, some books, you want to take your guitar and all those things, very difficult to pack it. If you only take some books, which you don't do, I know. If you take only books, you can nicely stack them. That is what I mean. So it is always better to have a single type of gate the design, that is why the universal gates assumes importance. But we will not use always NAND gates. We will use all gates and we know how to do it later on. I will give you some simple examples of converting everything into NAND gate. 1 or 2 examples we will do. Okay, that is NAND gate and NOR gate, universal gates. Now, we have any questions? Mr. Kannan, can you unmute?
Yes, sir, I am doing it now.
Yeah, because I will ask them some questions and do some exercises.
I have unmuted everyone, sir.
Yes. Do you have any questions?
No, sir.
No questions. See, there are only two possibilities. One is that you understand everything, or you don't understand everything, you are sleeping. Which of them is true?
Understood. First one.
First one.
First one.
Thank you.
Yes.
Very simple stuff, guys. These are kid stuff. Today, the 4th standard guy will tell you all this. You don't need a professor of 40 years experience. Okay. Anyway, it's all the physics books in your high school class. Anyway, we'll get tougher, don't worry. It's not going to be like this. Okay.
Sir, I want to pass on one information to everyone.
Yes.
From today onwards, there will be a live webcast of all these lectures, sir. People who are unable to access the lecture by some means or the other, they can go to the NPTEL website, click the link and view the live webcast. It will be the same as like this, except that they cannot interact with the faculty, but they can even get it on their mobile phones or any of the iPods or anything like that, sir. They need not register, no need to just log in with your name or something. It's just a live webcast.
So, do you think they will do it and listen to some good music? Are you fools?
Yes, sir.
You listening to digital lectures in front of their girlfriends or boyfriends? Okay. Now, I want to ask some questions on the assignments. And if you are not able to, so you have to be interactive now. You have to tell some, raise your hand and give the answer. I will follow it up and then explain to the whole class. That will be nice. In another 15 minutes, we will do it. Okay. Are you all right? What is this Alpha College now? Alpha.
Alpha College.
Alpha College become Beta now.
Alpha College, Gauri, are you online?
Are you online?
I see them connected, sir. I see them connected, but I don't know whether they are able to hear me, but they are connected.
Okay, well, we are not able to hear you, you are not able to hear me either. That means they look at my face all the time, which is not pleasant. Somebody is crying, baby, cry baby.
No. Yeah, that is why I prefer to mute them also. There's a question from Subhash College, Kolkata. Netaji Subhash College, Kolkata. There's one question, sir.
Put your hand up and ask the question.
Please introduce yourself and ask the question.
Yes, Subhash.
Sir, I am Subhasis Bhandari from Netaji Subhash Engineering College. Sir, I wanted to ask that for reducing the size, we use the two gates, NAND and NOR gates. Sir, for reducing the size of the circuit.
Yeah. And then convert them into NAND gates. See,
Okay,
any function
sir,
given to you, you first implement using AND or invert. These are required gates, fundamental gates. But then having done so, when you are going to manufacturing, it becomes too much difficulty. We have, let us say 50 AND gates, 30 OR gates, 25 NOT gates, instead of the 3 varieties. If you can reduce all of them to NAND gate equivalent, I will end up with 150 NAND gates, which is easier for me to manufacture. Cost wise it is nothing, because IC is so cheap, manufacturing is so cheap. The cost you are paying is for the engineering, the design, the tools they use, time of the engineers, and the profit of the huge multinationals, all that you pay. But finally, when you look at this circuit, it will cost you hardly 10 paisa. Okay? That is the concept.
Okay, thank you, sir.
Right. Now I'll ask you some questions on the assignment. Assignment is already
Sir, I
there
have
on the
a
lab.
doubt.
Did you see that?
Sir,
Assignment
I
1
have
is
a
on.
doubt from you.
Who is this, sir? Someone has got a doubt.
Yeah.
Sir, this is Archie.
She's Archini, sir. Archini is
Yeah.
once has a doubt.
Yeah, I know.
Sir, I have a doubt from the assignment itself.
Ah, tell me, which problem? I don't have the sheet here.
Sir, sir, there's one question where one base is unknown.
Ah, that's a good question you did. I'm not going to tell you the answer now. And the solution will be given to your mentors anyway. You are supposed to try it out before. I can't just go and answer all the questions. What is that? You getting an echo?
Yes,
Krishnan,
sir.
I'm
Sir,
hearing echo. Kannan.
so
Oh, okay, sir.
I'm getting echo from what I talk.
Oh, I don't know from whose line it is. I don't know. Someone has not cancelled his echo cancellation
Okay.
in this configuration setting.
Okay. So that question you try. We'll give you the answer. Anyway, solutions will be also posted. Okay? If we give the solution now, then there's no incentive for you to work. Okay, let us start with a simple question. We talked about ASCII codes. Remember ASCII codes? Right? First of all, I want to tell you something which I forgot in the codes. There's a code called BCD code. You might have known by now. In binary, there are 16 positions, 4 bits, 16 positions. I can go from 0 to 15. So 0 to 15 hexadecimal. 0 to 15, 0, 0, 0, 0 to 1, 1, 1, 1, up to 0, 1, 0, 0, 1, the 0 to 9, and from 1, 0, 1, 0, just 10. 10 is not a single digit, it's 2 digits, so I put a B, C, D, E, F. 6 last digits, last 6 will be alphabets, ABCD. This is called hexadecimal. So in 4 bits I can represent 16 numbers. But in BCD we want only 0 to 9. BCD means binary coded decimal. Binary coded decimal. So I want 0, 0, 0, 0 to 1, 0, 0, 1. We don't use these things. Even though there are 4 bits, we don't use this in a BCD code. Now, the computers you represent calculator, you are like to have digital numbers. Even though the computer takes it into binary, does all the arithmetic and spits you the result in digital, decimal, you enter decimal numbers, the result is decimal number, the inside is all binary. Such a thing is called BCD. Suppose I give you a number 73. If I want to convert it into binary, I will keep dividing by 2, 2, 2, 2, 2. Now I don't do that. This is to BCD. I will take each digit and represent it binary. This is 7, this is 3. BCD representation of 73 is 0111 for 7, 0011 for 3. Okay? That you should know. I forgot to mention this the last time. Now, all of us know the ASCII codes. 7 bits followed by a parity bit. So I want you to write digital. In ASCII code, or it's too large a number, you say data. In ASCII with even parity. even parity, I told you this morning, I mean in the beginning of today's lecture, what is parity, how do you know even, how do you define even parity, how do you define, all that I explained now. So now data is the, I am typing data in the computer, and how will it be stored as ASCII codes with even parity? You understand the question? Quickly, do it. What are you sitting for? We have a piece of paper and a pen. Well, I can help you with A to C. A is 40, I think. A is 41 hexadecimal. B is 42, etc., etc. Add 26, you will get Z. 41 is the starting of A for uppercase. For uppercase A, code is 41, hexadecimal representation. Now, so what will be D then? A, B, C, D, 44. 1, 2, 3, 4. So this is 44 hexa, which is, no, I'm sorry, 44 will not be represented as this. The hexadecimal 44, how do you represent it? In BCD, I think I have done it. In BCD, it is, in BCD, is 0, 1, 0, 0, 7 bits. Now I want even parity. Already there is even ones, put a 0. This is 8-bit BCD representation of ASCII code, letter D. Data A is 41. 41. Even parity. T, I have to find out. Somebody has to count it. Digital, I think I have D, T. T is 49. No. T is 54. T is 54. 54 is 54 BCD. Parity even, then only odd numbers, put a 1 here. This I already wrote. So the data that you represent in a keyboard, if you want it to be read as a BCD number in the computer with an even parity, it will be read as D as 44, but each digit, we don't convert 44 into binary. If you convert 44 into binary, it will be different number. Divide by 2, 22, divide by 2, 11, divide by 2, 5, divide by 2, 4, divide by 2, 2, divide by 2, 1. Then it will be 1, 0, 1, 1, 1, 0, 0. It is not like that. It is 4 separately as a digit, 4 another 4 separately as a digit, 7 bits. This 7th bit, this one we only use 3 bits for the first number, because we want only numbers will be like that only. Then I add a parity bit is even parity, 2 ones, so it's 0. That is it. Simple. Use of codes, I thought I will give an example. Now, binary to gray code conversion, I will ask you a simple question. You know that, I am sure. These are all exercises. I had a binary to gray code. I have 1 0 1 0 1 0 1 in binary. What will be the gray code? Can someone tell me quickly? Yes. Unmute please this person. Yes sir. Because she wants to give me the answer. First time I am hearing an answer from them. I am happy to listen.
Yes, sir. Actually, you can go ahead, please.
Yes, please tell me.
So 1110111.
You are talking from here, huh? 1110.
0111.
How did you get it? How did you get it in the gray code?
Sir, I converted it to the table like which you taught in the last class and I matched it up.
Okay, that is one way of doing it, but that is not correct answer because it's very easy to do it. I will tell you now. Now that you know exclusive OR gates, you take 2 bits at a time. Okay? I have so many masters. 0 1 the exclusive OR. See, first you copy this. Binary last one is same as gray one, right? Then you take the exclusive OR of this. That will be the next bit. Exclusive OR of this. What is exclusive OR? When one is a 1, the other is a 0, the output is 1. When both are 1s or both are 0, the output is 0. Exclusive OR of this and this. This is gray code. But I will give you a number which is not going to be 1111, then you should not think that all gray codes are 1111. I will give you another example. 110 0 110. Let us do this. Gray code. This is 0 is copied. 0 1 exclusive OR is 1. 1 1 exclusive OR 0. 1 0 1 0. So you take 2 bits at a time. First bit you copy. Every time else you take 2 bits at a time and then get the exclusive OR number. If it is 0, both are zeros, put a 0. Or both are 1s, put a 0. If one is a 0, the other is a 1, you put a 1. Simple. This is also the homework. Okay, what is the 9th complement of 6582? In decimal number. You always put a base here. You should understand whether it's a binary or BCD or hexadecimal. Hexadecimal also without A, B, C, D there can be a representation. So you don't know when number is given, you should know whether it's a BCD number, a binary number, a decimal number or a hexadecimal number. So you always put the base there. So what is the 9th complement of 652? What do you do? Yes. That friend from where I forgot.
3417.
She should not think only boys are smart. Girls are smarter than boys. Okay, tell me.
Sir, the answer is 3417.
You subtract from 9199. Fine. This is 9th complement of 658. So you got a feel for the first assignment, first question. Second assignment will start with the gates. We will do it after some time because we have to cover a lot of material before we are ready for an assignment on this. So another 2-3 classes it will take before the next assignment comes. So now I am signing off, and any questions I will answer. Otherwise, the class is dismissed.